So now what we want to do is go into the mechanisms. So how do these things work? What are the key mechanisms that take place here? What we want to do is simplify this model further and use a simple kind of a matchstick. So if you look at the little picture on the far right, you have a matchstick with the head being water repelling and the stick being water attracting. The head part is positively charged, the tail part is negatively charged. And so you may want to write that on a piece of paper because we're going to use that little model over most of the next 7 mechanisms that we look at here. Now the first mechanism that we want to look at is the interaction between liquid carbon and hydrated particles. So imagine you have a soil particle that already has some amount of moisture to it. When you add liquid carbon to this, what happens is you get what's called a hydrophilic mechanism. The humics will, through Brownian motion, they will begin to organize themselves around the edge of that hydrated particle around the water. So what happens is as you add more moisture through irrigation or through natural rain and watering, the water comes down, by gravity in through the ground and then interacts with that interface. Now, when we talk about forces here, they're relative. So, for example, in this case, gravity, the gravitational force of the water is greater than the hydrophobic, hydrophilic forces of the humic. So what happens is the water interacts with that interface. That humic interface is disturbed. Water increases around the particle, and then that hydrophilic orientation returns. And so it allows water to come in, and then it returns, and that particle swells further. So what you get is a thicker layer of absorbed water or higher hydration. You get higher water holding capacity, less water evaporation, higher water availability for plants, and hydraulic repelling forces. I'm going to talk about a couple of these and what they mean here in a minute. For example, like hydraulic repelling. The second mechanism that I want to look at here is the interaction with dehydrated particles. So imagine a sand particle that has very little hydration to it. When you add liquid carbon to it, you get a hydrophobic mechanism that takes place around that particle. And so what happens is, as water begins to interact, it begins to be attracted by the hydrophilic portions of that particular humic. And so the humic coats the particle, and then it begins to attract water around it and hold that water. So you get a hydrophilic surface formation. You get a higher rate of surface hydration. You get sodium cation activity and toxicity suppression. Again, you get higher hydraulic repelling and higher electrostatic repelling under rehydration. Now, I'm going to talk about a couple of those mechanisms next here. So if you say, what keeps the particles hydrated? If you look at the picture on the left and you see those 2 light blue dots, those would represent, let's just say, water molecules. Now, because of the motion of those molecules, they're constantly bumping into each other. Under normal circumstances, some of those molecules, as they bump into each other, get ejected. And so that leads to evaporation. But when you have this humic surrounding this humic layer surrounding that water, more of the water gets held in. It keeps the water from escaping. So it almost acts as a filter to keep some of that water from escaping out into the atmosphere. So you get more of that water staying around the molecule. Not all of it. So if you had an extreme drought over weeks and weeks, there's nothing that can help you in that case. But what this will do is keep that particle hydrated for for a much longer period of time. Now, if you look at hydraulic repelling, as these particles begin to get more and more hydrated, they will swell. And as those particles swell, they begin to have hydraulic pressure against one another. That hydraulic pressure is one of the mechanisms that helps the compaction of the soil and the increase in porosity. Now we want to talk about electrostatic repelling. So in this particular case, you have these particles that have negative charges on the outside of them, relatively speaking. And so as these particles begin to come in contact with each other, there is a natural electrostatic repelling force, just as if you took the two same poles, like poles of a magnet, and begin and try to push them together. There would be that repelling force. And so this, again, is one of the mechanisms that enables decompaction within the soil. Now, the third mechanism that we want to talk about is flexible bond or bridges formation. So in this particular case, you have soil particles. Let's consider these to be fine particles in the soil. You also have mineral cations that are surrounding it. When you add liquid carbon to it, you create a particle aggregation mechanism. And so what happens is the humics bind to both the cations in the soil and the particles. So you create these flexible bridges between these particles. These flexible bridges help with aggregation. So you instead of having a soil that has lots of very tiny particles that are highly compressed together, you begin to create these flexible bridges and aggregation of particles. So this helps in valuable soil structure formation and restoration, small particle aggregation, and optimal soil porosity formation. You also notice that under drought conditions, you begin to see the soil crack, and this particular mechanism will help to mitigate that situation somewhat. Now, the next two mechanisms that we talk about deal with biological activity. And so this picture here describes how fulvics and humics interact with, for example, a typical plant cell differently. So if you look at the fulvic acids, because they're smaller, they have the ability to penetrate cellular walls and enter into the cell. In doing that, they have the ability to bring in nutrients. They have the ability to stimulate the metabolism within that plant cell structure. However, too much fulvics can bring in toxic metals and other things. So if you have too much fulvics, that's not a good thing. The humics, however, because of their size, they tend to bind or stick to the outside of the cell structure. If you have too much humics, they can end up starving that cell. If you have just the right amount, they end up protecting the cell. They protect it from too much fulvics entering in. They protect it from pathogens, from toxins in the soil, and other things. So what you want to do here is have the right balance between humics and fulvics so that you are stimulating the cell and protecting it at the same time. So when we look at mechanism 4A, this is the stimulation of native soil microbiology. So in this case, we're talking about heterotroph bacteria. You add liquid carbon into this. These heterotrophs typically use organic matter. Fresh organic matter is a carbon source. This stimulates the bacteria. I'm talking about liquid carbon. It stimulates growth of the bacteria and replication. And so what happens is these bacteria grow, they increase biomass because of their growth and replication, and they release carbon dioxide. This is a natural process, so we're not creating more gas, but that gas that's released is a mechanism for helping to decompact the soil. The increase in biomass gives volume to that soil and gives biomass into that soil structure. There are other types of bacteria, such as autotroph bacteria, which are also stimulated by liquid carbon. However, they use carbon dioxide as a carbon source, and so they're absorbing carbon in this case. So in this particular mechanism, biomass formation increases in that soil, resulting in volumetric extension, resulting in increased soil structure, improved soil structure. Mechanism number 5, this may seem like a trivial mechanism at the outset, but it is actually a very important mechanism. We have found over and over that liquid carbon stimulates the attraction of earthworms. And so what happens is the areas that are treated with liquid carbon, you have an increased activity and a migration of earthworms into that area. Those earthworms create channels. Those channels allow gas exchange. They allow, water to penetrate deeper into the soil. They decompact it. They create biohumus, which has available NPK at a small level. They increase the overall biomass within the soil. And so these are very important for aeration, irrigation, drainage, and the restoration of degraded soil. We had a terribly dry drought condition in our area last summer, and I took, at the end of the summer, liquid carbon and put it on a portion of my yard that was as hard as a rock. It was extremely compacted and dry. And I noticed the formation of these structures all over my yard. It began to become very spongy, and I saw these formations. I didn't know what they were, and I brought them in, and Dr. Shulgin and Dennis identified them as worm castings. And these castings were all over the yard. So this showed a rapid increase of worms entering into that particular area of my yard and beginning that decompaction and softening process. And so these channels also help with rain, excessive rain, to allow it to better drain through the soil.